Hey everybody, welcome to another video. In this video, I'm going to teach you a different uh, integration technique we have seen. So far, you've seen integration by parts, tricks of integrals with different powers of trig functions, um, and the like, right? This is another integration technique that we will see. And it's what's called partial fractions decomposition. So here is the origin of this technique, right? This is where this comes from. So we got to go back to learning about how to add fractions, right? So if I want to add, let's say 1 equals x minus 2 plus 1 over x plus 1. Well, what do we do? Well, we have two different numbers in the denominators of each of these fractions, right? So the primary goal of adding fractions is making sure we get a common denominator, right? So what we can do is, since each of these factors in the bottom are different, right? What we can do is multiply each of the fractions by the opposing factors. So for example, 1 over x plus 1, we want to multiply the numerator and the denominator by x minus 2, right? By x minus 2. And if I want to move this so I can have extra room, so that's better. And then I want to multiply the numerator and denominator of this fraction on the first term by x plus 1. X plus 1 and then x plus 1. So what we will get is 1 times x plus 1, so that's x plus 1, plus x minus 2 divided by the product, x minus 2 times x plus 1, right? And then we can combine like terms, and then we'll get 2x plus 1 in the, I'm sorry, 2x minus 1. 2x minus 1 in the numerator, and the denominator will be just x times minus 2 times x plus 1, right? And that's how we would add fractions, okay? With partial fractions decomposition, we want to reverse this process. We want to reverse the process of adding fractions, okay? So in other words, we want to start off from the end product, and we want to separate one fraction into two, right? And here is the procedure and how to do this, right? So if I start off with the end result, right, 2x minus 1 divided by x minus 2 times x plus 1, right? So this one fraction, well, it's equal to a sum of the fractions that have the two opposing factors on the bottom, right? So if you look at it, right, this whole fraction, this is equal to a constant, a over x minus 2 plus another constant, b over x plus 1, right? Okay? So from here, we want to solve for a and b, right? A and b. Okay? So just making sure it looks good. And so what we're going to do is we want to multiply both sides by the common denominator on the left-hand side. So x minus 2 times x plus 1 on the right. And we want to multiply the same value, right? So x minus 2 times x plus 1, right? So what we will have is we'll have 2x minus 1 equals to a times x plus 1 plus b times x minus 2. Okay? All right. Since these two equations have to equal, right, we can combine like terms and set the coefficients for x equal to each other and the coefficients for the constants equal to each other, right? That's one way. The other way is we can pick out different values for x, right? So if I let x equal to, let's say, -1, right? X equals -1. On the left-hand side, this would be 2 times -1 minus 1 equals 2. Well, when x is -1, this will be 0, right? Plus b times this will be -3, right? Okay. So we'll have -3 equal to -3b. And then to solve for b, we know that b is equal to +1, right? We know that b is 1. Likewise, if we just pick another x value, let's say x equal to 2, that's a good one. If x equals 2, right? On the left-hand side, we'll have 2 times 2 minus 1 equals to a times -2 plus 1 plus b times 2 minus 2, which is 0. So the coefficient on the b's will be 0. So b goes away. So we want to solve for a here. So we'll have so I want to make sure I don't make a mistake. So this is 2 here. Right, so this is 2. So 3 is on the left, and we'll have 3a on the right. So that means a is 1. And it checks out too, right? From the example we had before. Okay? So in other words, we can rewrite 2x minus 1 divided by x minus 2 times x plus 1 equal to, well, 1 over x minus 2 plus 1 over x plus 1. And that's the idea of partial fractions decomposition. Okay? The steps are a little bit cumbersome, but here is the procedure for partial fractions decomposition. Okay? So throughout these problems, we're supposing that our function is equal to a rational function, right? P of x divided by Q of x. Where P and Q are polynomials with no common factors, right? And the degree of the numerator, P, is less than the degree of the denominator, right? So the highest power on x for P is less than the highest power on x for Q, right? So if we assume that we can factor out Q as a product of simple linear factors, so it's like with this expression right here, these are called simple linear factors, right? Linear factors, right? This is what we would do, okay? So step 1 is we want to factor out the denominator as much as possible, right? So we want to factor out the denominator Q in this form that is written out as n simple linear factors, right? So they're distinct, okay? So there's no repeats. Okay, so one of the cases is if you have factors that don't repeat, okay? I'll go over in another example where we have factors that do repeat, okay? So that's step number 1. Step number 2 is to write out the partial fraction decomposition by writing the fractions in this form, right? A1 through AN are constants. So they're any real numbers, right? R1, R2 through Rn, these are the distinct real factors of Q of X, right? So we want to write it as A1 divided by X over R1 plus A2 divided by X minus R2, and so on. Okay. I can't see my work with this screen in the way. So the third step, step number 3, is to clear the denominators from both sides of this equation here in step 2 by the product of those factors, x minus R1 times x minus R2, all the way up to x minus Rn. Okay. Thereby, you can produce conditions for each of the constants A1 through AN, right? And then you can solve for the coefficients A1 through AN by just plugging in different values for X. That's one way. You can use a little bit on linear algebra to gather up the coefficients for the X, to gather up the sum and difference of the coefficients for each power on X, right? And so you can also use, in some cases, using the elimination or the substitution method, but you can also use linear algebra to use row reduction, right? But if all else fails, you can plug in different values for X, and you'll get unique, distinct values. Well, you'll get values for each of the A sub n constants, right? So let's look at an example on how we would do this, okay? So suppose I want to integrate this function, 1 divided by x squared minus 5x plus 6, okay? Well, there's several ways to integrate this. We could use trig sum, right? But that would involve completing the square on the denominator, and it would be a little bit messy, right? But if you notice, the denominator is factorable. So I want you to work out this example on your own, and I'll go over the solution to how to do this, okay? Okay, so I think you had some time. So what we want to do is factor out the denominator, right? X squared minus 5x plus 6. Now, x squared minus 5x plus 6, well, we want a number that multiplies to be 6, and they add up to be negative 5, right? Well, those factors of 6 would be x minus 2 and then x minus 3, right? Okay. Negative 2 plus negative 3 is negative 5, right? And then negative 2 times negative 3 is positive 6. So we can rewrite this integral as 1 divided by x minus 2 times x minus 3, right? Okay. And so we want to perform the partial fractions decomposition for the quantity 1 divided by x minus 2 times x minus 3. Okay. X minus 2 and x minus 3 are distinct linear factors, right? Linear because you have x minus a constant or x plus a constant, right? So what we want to do is we want to set, let's say, A1 over one factor, let's say x minus 2, plus the other factor, we'll call it A2, right? A2 over x minus 3. Okay, A2 over x minus 3. All right. So what we want to do now is solve for A1 and A2. Okay. So this was what did I say? Okay, so this right here was step 1 to factor out the quadratic. This is step 2, right? And then step 3 is to multiply both sides of this equation by the product of those factors, right? X minus 2 times x minus 3. Okay? So this is step 3. And so we'll have 1 is equal to a1 times x minus 3 plus a2 times x minus 2, right? X minus 2. So, okay, so let's just go up here. I can plug in different values for x here in this equation, right? So if I pick x equals 3, right? This equation will turn out to be the following. 1 is equal to, well, a1 times 3 minus 3, so that's 0. So we'll have a2 times 3 minus 2, which is 1, right? So therefore, a2 is equal to 1, right? Also, if x equals to 2, right? If x equals 2, the equation becomes the following. We'll have 1 is equal to a1 times 2 minus 3, which is -1, right? Plus a2 times 2 minus 2, which is 0. So we'll have a1 is equal to -1, right? a1 equals -1, right? So what we have here is the partial fractions decomposition, right? So therefore, the integral of 1 divided by x minus 2 times x minus 3 dx is equal to the integral of, so a1 was -1, so -1 over x minus 2 plus a2 is 1, so 1 over x minus 3 dx, right? Okay. In each one of these, they become a very straightforward integral, right? So in this case, this integral will equal to the integral of -1 over x minus 2 dx plus the integral of 1 over x minus 3 dx. And so this equals to minus the natural log of the absolute value of x minus 2 plus the natural log of the absolute value of x minus 3 plus c. Okay? And that is your final answer, right? Final answer. So this here is just one example of a integral that has simple linear factors, right? They're distinct, like this one. What about another example that deals with a repeated factor? Well, so in the case of a repeated factor, we're going to have to take account of the repetition of that factor occurring in the fraction. So the procedure for this is the following, right? Suppose we have a repeated factor of this type, x minus r to the m. So m is any real number, right? R is just a factor, okay? So suppose it appears in the denominator of a proper rational function that is factored, right? And it's reduced, okay? The partial fraction decomposition has a partial fraction for each power of x minus r, up to and including the nth power, okay? So each time you have to add in an extra power for that factor x minus r. So like this, okay? So we have a1 divided by x minus r plus a2 divided by x minus r squared plus a3 divided by x minus r cubed plus a4 divided by x minus r to the fourth, and so on, right? All the way up to a to the m over x minus r to the m power, right? And then we will determine each of these constants, a1 through am, similar to the previous example, right? So let's see if we can work out this example, right? Try to work out this integral. So suppose I have this one, 16x squared. Let's see if I wrote this down right. Okay, I meant 16 over x minus 6 times x plus 2 squared. Okay, here's one example. I want you to figure out how to proceed with this integral, right? So pause the video and try to work this on your own. Okay, so I guess you had some time to go over this example. If not, that's okay. I'll go over this in its entirety. So what we have here is we have one separate factor, x minus 6, and we have a repeated factor, x plus 2, right? So first, right, the denominator is factored, so good, that's step one. So the partial fractions decomposition, right, is the following. So if I have the left-hand side, 16 divided by x minus 6 times x plus 2 squared. Okay. First, we have one linear factor, x minus 6. So that would be one coefficient, a over x minus 6. So capital A is just any constant, right? Next, we need to look at the, let me actually color code this. Let me write this in green. Okay. A over x minus 6 plus, we have a repeated factor now of x plus 2 squared. So now we need to add in 2 fractions for each power on up to including 2, right? So we need to write in plus b over the first factor, x plus 2, plus c over x plus 2 squared, and we stop. Okay? 2 is the highest power on x plus 2. And this is how you write out the partial fractions decomposition for this rational function here. Okay? Next, we multiply both sides by the product of those factors. So x minus 6 times x plus 2 squared on the left and on the right. Okay, so we'll have 16 is equal to a times, we'll have x plus 2 squared plus b times x minus 6 times x plus 2 plus c times x minus 6. Okay? All right. So that's just the algebra here. So what we want to do now is solve for A, B, and C, right? So we can do this by plugging in different values of x. So if x equals -2, let's start off with that. So if x is -2, we'll have 16 on the left, and on the right-hand side, the a will cancel, and the b's will cancel. So we'll have c times -2 minus 6, right? So that gives us a -8. which leads us to saying that c is equal to -2, right? C is -2. Okay. How about when x equals to another nice number? Let's say 6, right? So if x is 6, the b, so we'll have 16 on the left-hand side. And on the right-hand side, the b term and the c term will cancel. And then we'll have a times 6 plus 2 squared. All right. 6 plus 2 squared. So that would be 64. So this would lead us to saying that a is equal to 1/4. A is equal to 1/4. All right. And to figure out what c is, well, we can just plug in another number, right? How about 0? That's another great, nice number. So if x is 0, we'll have 16 is equal to, we already know that c is -2 and a is 1/4. So this is 1/4 times 2 squared, right? 2 squared plus, we don't know what b is. So b times 0 minus 6, so that's a -6, times 2 plus, we know what c equals 2, so that's a -2, so plus -2, so that's a -2, -2 times -6, right? -6. So this equals to 1. So 16 equals 2. 1 minus 12b plus 12, right? And what I will get here is that b is equal to -1/4. If you solve this, b is equal to -1/4. So what we did here is that we can rewrite this integral that we were given equal to the following integral of these functions. So a is 1/4. The integral of 1/4 over x minus 6, okay, minus 1/4 divided by x minus 2, x plus 2, excuse me, plus, or I should say minus 2 divided by x plus 2 squared dx, okay? The first two terms will involve a natural logarithm. So this equals to 1/4 times the natural log of the absolute value of x minus 6 minus 1/4 times the natural log of the absolute value of x plus 2, right? The last one, we're going to have to use the power rule for exponents. So this is -2 times -1 over x plus 2. So this is plus 2 times 1 over x plus 2, right? Because as a note, u minus 2 du. Right, this is equals to 1 over -2 plus 1, u to the -2 plus 1. -2 to the -1. Yeah, okay. So that's the power rule for integrals. And then plus c. Okay. That's the final answer for that one. Okay, so hopefully you like that one. So again, this is all partial fractions here. Solve for the coefficients and then rewrite one integral as a sum and difference of integrals, right? Okay. First two becomes a logarithm integral, and the last term is a power rule integral, right? So hopefully that made sense. The other case I want to talk about is if we are dealing with factors that are irreducible, right? So quadratic trinomials in particular that are not factorable. Okay, so they're called irreducible. So here's what we do. Okay, partial fractions with simple irreducible quadratic factors, right? So suppose we have a factor that looks like this, ax squared plus bx plus c, but it's not factorable. It's in reduced form, right? Okay. In that case, the partial fractions decomposition would be the following, right? We need to tack on a capital A times x plus a constant, capital B, for each irreducible quadratic factor that occurs in our integral, right? The A, so the coefficients on x squared and the coefficients of the constants will be determined by going through the partial fractions algorithm, right? So, like this example here, I want to go over this one. Try to work out this example. 10 divided by x minus 1 squared times x plus 1. Okay, this is an example. X squared, excuse me. So as you know, x squared plus 1 is irreducible, right? It's an irreducible quadratic, right? Okay. And then another example of an irreducible is this one, right? You cannot factor any anymore, right? So yeah, so nevertheless, x squared plus 1 would be a quadratic that we cannot factor any further, right? So try and pause the video and try to work on this problem. If you're stuck, that's okay. I will work out the solution in a few minutes. So good luck. Okay, so I think you had a good try with this example. So what we have here is we have one repeated linear factor of x minus 1. And this here is the irreducible quadratic, x squared plus 1, x squared plus 1. Let me write that out a little bit clearer so you can see it. X squared plus 1. Okay, so first off, now if you see a denominator factored like this, well, it's in factored form. So step one is making sure that the denominator is factored out as much as possible. We have that in this case. All right, so now we want to look at the partial fractions decomposition, right? Partial fractions decomposition of this fraction. 10 divided by x minus 1 squared times x squared plus 1. Okay. X minus 1 is a repeated factor, so that means we need to add in two fractions for each power of x minus 1, right? So we'll have a over x minus 1 plus b divided by x minus 1 squared, right? So that takes care of, let me color code this in green. So a over x minus 1 plus b over x minus 1 squared, right? Then we needed to take care of the irreducible quadratic factor. So in this case, it's x squared plus 1. So we need to tack on a cx plus d term in the numerator divided by x squared plus 1. Okay? So this right here, this would be the partial fractions decomposition for this fraction, right? So now what we want to do is multiply both sides by the denominator, x minus 1 squared times x squared plus 1. So we'll have that 10 is equal to a times So we'll have an extra x minus 1 factor times an x squared plus 1 factor plus b times the x minus 1 squareds will cancel and you'll get x squared plus 1, right? Plus the cx plus d term times x minus 1 squared, right? X minus 1 squared. So, now I'm going to show you the other method for this one to figure out how to solve for A, B, C, and D. So solve for A, B, C, and then D. Okay. So one way is, okay, so we want to group together the coefficients regarding to the highest power on X, right? Let's see. Okay. So 10 is equal to A times. So this would be x cubed plus x minus x squared minus 1. That's the A term. Plus b times, well, bx squared plus 1. Plus, okay. Cx squared minus, oh, wait. I got to factor out bx minus 1 squared. So cx plus d times x squared minus 2x plus 1. Plus 1, right? And so this means that 10 is equal to a times x cubed plus x minus x squared minus 1 plus b times x squared plus 1 plus cx squared minus 2 cx cubed, excuse me, cx cubed minus 2cx squared plus cx plus dx squared minus 2dx plus d. All right. There's that. Okay. So all we can do from this point is to match up the coefficients on x cubed, x squared, x, and then our constants. The good news is there is no coefficients for the x cubed, x squared, and then the x power, right? On the left-hand side. All we have is a constant 10. So that makes things a little bit more simpler to work with. So we'll have, so for the x cubes, so if I just, and then this is my constant, right? And actually, I don't want to do it that way. Okay, so for the x cube terms, we have an a, and then we have a c term. A plus c equals 0. Okay. For the x squared terms, we will have a minus 2a. We have a plus b. We have a minus 2c. And then the plus d, which is 0. Okay, for the x terms, I have an a here. No x's for b. I have a c here, and then a minus 2d. Minus 2d, and that's 0. And for the constants, I will have a minus A plus B plus B and a plus D. Okay, so we'll have four different equations for each of the coefficients, right? Um, right away in equation one, we can say that C equals minus A, right? C equals minus A. And what else can we say? We can also say that in the third equation, we have that A plus C is minus A, so this is minus A. Minus 2D is 0. This says that D is 0. Okay. Since D is 0, in equation 4, we will have minus A plus B is 0. So B is A. Okay. And so D is 0. B is A and C is negative A. So the last equation will have minus 2A plus A minus 2 times minus A. D is 0, so that equals to 0. Okay, so and okay. Um Man, did I make a mistake? Let's uh that's uh oh yeah, I made a mistake. Yeah, so this is minus A. And okay. Plus B minus 2C plus D. Right. Okay. And the X's. So A plus C and minus 2D. Okay. I have to make sure this is right. Minus A plus B plus D. Okay. So, all right. So going back from the top, so C is minus A, and uh, and this would lead us to saying that D is 0 here. Okay. And I have here that B is A, and in equation 2, uh, Ah, that makes no sense. Okay. Minus. And, oh, shoot. Okay. This is the thing where we have to really keep track of your algebra. So, okay, so I'll have ax cubed plus ax, or I should say minus ax squared plus ax minus a plus x squared plus b plus cx cubed minus 2cx squared plus cx plus dx squared minus 2dx plus d. Okay. Ah, okay. I see the problem. So I need to gather up the x cubed, the x squared terms, the x's, and my constants. Okay. So a plus c is 0. So minus a plus b minus 2c plus d is 0. The x terms is a, and there's no x terms there. So plus c plus or minus 2d. And then minus a for the constants. I will have so minus a plus b plus d equals 10. Forgot that. Okay, now it should be able to work. So from the first equation here, so 1, 2, 3, and then 4. So in the first equation, we'll have c equals a, right? And from that, from the third equation, I'll have a plus, or c equals minus a. A plus minus a minus 2d is 0. So this forces that d is 0. So, okay. In equation, well, in equation 4, rather, d is 0. So, so we'll have b is equal to 10 plus a, right? And then in equation 2, right? So this is minus a plus 10 plus a, that was b, minus 2 times minus a plus d is 0, so that's 0, and the right hand side is 0. Okay, and minus a plus a, they cancel, and this leads us to saying that 10 plus 2a is 0. And then a is equal to minus 5. Okay. A is equal to minus 5. So that means c equals 5. And b is 5. Okay. B is 5. All right. So sorry, that took a while. So the integral of 10 over x minus 1 squared times x squared plus 1 dx is equal to, well, a is minus 5, so minus 5 over x minus 1 plus 5 over x minus 1 squared. And then d is 0, so this would be minus, I should say plus 5x divided by x squared plus 1 dx, right? Okay, so the first one is a natural log antiderivative. This second term would be minus 5 over x minus 1, right? The last one is a straightforward u substitution. So plus 5 divided by x over x squared plus 1 dx, right? So the last one is a u sub. And so this piece in u's, this is equal to 5 halves du over u, which is 5 halves the natural log of the absolute value of x squared plus 1 plus c. Right, so altogether, this equals to minus 5 times the natural log of the absolute value of x minus 1 minus 5 divided by x minus 1 plus 5 halves times the natural log of the absolute value of x squared plus 1 plus c. So that's the final answer. Sorry that took a while. But yeah, so this is the work. So hopefully that made sense. So this is the other way to solve for the coefficients A, B, C, and D, right? Yeah, so one more example I want to go over involves with a case where the numerator is not less than, the degree of the numerator is not less than the degree of the denominator. So how about looking at this example? X cubed plus 2 divided by x cubed minus 2x squared plus x dx. Okay. Try work out this example and see what you come up with. Okay. So we'll be right back. Okay, so hopefully you had a go at this example. If you notice here, the degrees of the polynomials in the numerator and the denominator are equal. Okay, so partial fractions only involves with the rational functions whose degree in the numerator is less than the degree in the denominator, right? So what we want to do is perform long division, right? So we got to do some long division here of polynomials. Long division of polynomials, right? So here's what we do, right? So the divisor is x cubed minus 2x squared plus x. And we're dividing this number, this polynomial by x cubed. There's no x squared or x term occurring in the numerator. So we can just replace them with zeros. So 0x squared plus 0x plus 2, like this. Okay? So x cubed here can go into x cubed here one time, right? One time, right? So x cubed goes into x cubed once. And 1 times x cubed minus 2x squared plus x is equal to x cubed minus 2x squared plus x, right? Okay. Then we subtract the first 3 terms in our dividend with the last 3 terms here. The x cubes will cancel. We'll get a positive 2x squared. Then we'll have a minus x here. That's when we want to bring down the positive 2. Okay. And as you notice, right, we have an x cubed in our divisor and an x squared in our remainder, right? So we can rewrite x cubed over x cubed plus 2 divided by x cubed minus 2x plus 2x squared plus x equal to 1 plus 2x squared minus x plus 2 divided by x cubed minus 2x squared plus x, right? So we want to replace the integral here with this quotient here, right? So this equals to the integral of 1 plus 2x squared minus x plus 2 divided by x cubed minus 2x squared plus x. Okay? Right? So if you notice the first term, well, that's pretty straightforward. We'll get an x, right? And all we need to do is integrate the second term. It's 2x squared minus x plus 2 over x cubed minus 2x squared plus x. Okay. All right. So now we have a rational function whose degree in the numerator is less than the degree in the denominator, right? So we can perform partial fractions decomposition for the second term. Okay. So step 1, we want to factor out the denominator, right? So this equals to x plus the integral of 2x squared minus x plus 2 over, well, we can factor out an x, right? And this would be x squared minus 2x plus 1, right? And this equals to x plus the integral of 2x squared minus x plus 2 over x times this is x minus 1 squared, right? It's minus 1 squared. So we have one simple linear factor of 0 and a repeated factor of x equals 1, right? So we want to use partial fractions decomposition for the term in the integral here, right? So 2x minus x plus 2 over x times x minus 1 squared equals to, one of them is a over x plus, we'll take care of the x plus 1 squared term, b over x minus 1 plus c over x minus 1 squared, right? Okay. Next, we want to divide or multiply both sides by the product of our factors, x minus 1 squared, right? So we'll get 2x squared minus x plus 2 equals to a times x minus 1 squared plus b times x minus 1 plus c times x, right? C times x. So we'll have 2x squared minus x plus 2 equals to a times, we want to group all the coefficients for x squared, x, and our constants together, right? This equals to x squared minus 2x plus 1 plus bx squared minus bx plus cx, right? So this equals to ax squared minus 2ax plus a plus bx squared minus bx plus cx. And that equals to 2x squared minus x plus 2. Minus x plus 2. Okay, so we want to group all of the x squared terms, the x terms, and our constants together. So in terms of x squared, we will have an a and a plus b, right? Plus the x terms, we'll have minus 2a and minus b, and our constants. Our constants will be plus a, wait, I forgot one, plus c, we got that one, and plus a. This equals to 2x squared minus x plus 2, right? So what this means is a plus b equals 2, minus 2a minus b plus c equals -1, right? And we know that a is 2, right? 1, 2, and 3 here. So we know that a is 2. So in equation 1, that means that b is 0, right? And we also know from equation number 2, we have minus 2 times 2. B is 0, and then plus c is equal to -1, right? So this is minus 4 plus c equals -1, and so c is 3. C is 3, B is 0, and then A is 2. Okay, so we'll have the integral of 2x squared minus x plus 2 over x times x minus 1 squared equals to a over x. A over x is 2 over x. Plus 0 over x minus 1 plus 3 divided by x minus 1 squared dx, right? So this equals to 2 the natural log of the absolute value of x plus, I should say minus 3 times minus 3 over x minus 1 plus c, right? So all together, right? All together, we'll have x plus 2 as natural log of the absolute value of x minus 3 over x minus 1 plus c. Okay, so that's the last example. All right. I want all of you to hand in these problems on D2L. Just to make sure you understand what I was talking about here. So 31, 37, and 57. Okay. So make sure you work on those. I hope these videos were helpful. As always, if you have questions, please let me know. I hope you enjoyed these videos, and thanks for watching.